Hello, this is Electronics for College 22nd Gallium. So actually, we talk about band gap theory, the basic of semiconductors. And we explain what the band gap is, and by understanding that, you will know why gallium and germanium and other stuff are so important. The role of those metal element in the semiconductor industry making chips. This is all based on this band gap theory. What band gap theory? Well, I will explain to you whole things. Over here, say when you have the metal like a copper, atoms has an electron around, and when crystal of metal is created, the orbit of electrons are way outside of boundaries. It's overlapping, and that means electron can move from this atom to another atom freely. So it's move around inside the metal. Okay, that's what it means, overlap. So it's so-called free electron. Electron can move from atom to atom anytime. So when you apply the voltage, the electron run from here to here. So that's why metals, a lot of metals are conductor. Now, silicon has atoms and has electron around, electron orbit. But silicon's distance is about 0.2 nanometer. Okay, and electron, this orbit is not really overlapping. There is a covalent bonding, means silicon has 4 outer orbit, 4 electron, and this electron together, it's become 2. This become 2. So 2 is 8 electron, and it's a stable formation. But this covalent, just like carbon, when carbon connect, make a organic material, make a long chain, it's all covalent bonding. So the electron doesn't move around, okay, but when you increase the temperature, then the atoms start vibrating and electrons start moving around more and more, and when it's reached a certain energy level, electrons start jumping from here to here to here, so on and so. Okay, so the silicon is in the beginning, when temperature is low, it's a insulator, it's not really conductor. When temperature goes up, then it's become conductor. So if you graph the current, we apply plus and minus, this is log scale current versus the reciprocal of temperature become like this. So its current is proportional to exponent the VE and KT. So depend on temperature, it can be conductor when temperature is high here, this side. When temperature is low, here become insulator. So that's why it's called semiconductor. Okay, so silicon is semiconductor. So how much you have to excite the electron by heat energy? So the electrons are in the orbit, then they don't move around. It's called the valence band energy level, and there is about 1.12 electron volt. The energy distribution of electrons, some are high energy, some are low energy, and whatever exceed 1.12 electron volt, it goes to conduction band, and here electrons start moving. So you hit electron and get energy go up to the conduction band, then it's conduct. The silicon is only some part of the electron is excited by temperature. The heat energy can conduct the semiconductor. Okay, so what's happened is you have more different combination of semiconductors. Not only silicon, you can mix with, say, gallium and nitride, the gallium and arsenide, so and so. Okay, so what's happened is, let's look at the periodic table, right? Carbon and silicon, they have 4 electrons at the outer electron orbit. Okay, germanium is also same as silicon, and this is the area you use. Okay, because it's 4 electron. Here the 3 electron, it's missing. So if you mix those as an impurity in the crystal, then there is a void of electron. It's called hole. And what's happened is you have gallium and silicon and silicon and silicon, so. And gallium has only 3 electrons, and there's no electron to stabilize to the next neighbor silicon. Okay, so that makes this electron is easier to get into this hole. So if you apply voltage between the both end of the crystal, then let's say this is a plus, this is minus. Electron could move from silicon to silicon easily, but it's go to this void hole, and there's a hole here again. Then the next silicon fill the electron here, so electron start moving this direction, so the current flow. Okay, the band gap picture, you have a conduction layer and this valence layers. There is a hole. This energy level is kind of between. Then what's happened is the valence layers, its electron get in and this get out here. If you have a many hole like that, this act like a intermediate step, so even lower energy electron can start moving using this hole. Okay, So gallium is important to make it conductor, somewhat conductor. The mechanism of conduction is the very important part. They have a extra electron, nitride, phosphorus, arsenide. What happens if you have those impurity in the silicon crystal? Silicon, say you have phosphorus. Okay, the phosphorus has one extra, so you have a covalent bond and one extra electron. So what's happened to this extra electron? Just like if you look at the band energy level, this is conduction and this is valence. The electron is kind of sitting here, and if you apply the voltage, the electron, since it's here, it's easier to move, go to the conduction layer with a little heat energy and move. So if you have many those impurity in the crystal, then there are a lot of this stepstone electron. The electrons go out and resupplied with the neighbor silicon. So there is a conduction aided by the extra electron. This is a conduction aided by the holes. So there are two types, and this kind of material we call N type, and this kind we call P type. Okay, so coming back here, there may be hole or electron in the material, right? So when you use a different combination like silicon and carbon or gallium and nitride, this gap can be larger. Okay, and like a LED emit light, the light energy is about 2 to 2.5 electron volt. So if you set the right, so what's happened is when electron is excited here and drop to valence band, it's release energy, and if this energy is right, like a 2.5 electron volt, then probably you see the blue light, green to blue light. So that's a LED. Okay, so by combining a different type of material here around the silicon, you can change the energy band gap, and energy band gap is just right energy level of visual light. It can be LED, and the solar cell is opposite. If you have this kind of material, and if lights come in and excite electron, kick it up to conduction layer, then it's move and cause the electricity. So light causes electricity. That's the solar cell, right? And now this gallium nitride, the higher energy required to move, that means it can handle higher voltage. And the gallium nitride is very popular right now because the energy IC chip for the EV require higher voltage, like 30 volt to 150 volt. So using gallium nitride, it can handle the higher voltage. And another characteristic is switching speed tend to be faster than just silicon based transistor, like a gallium arsenide, gallium nitride. So switching speed is so fast, communication device. Use those semiconductor chip. Okay. So basically, that's the theory of the semiconductors. When this become very high, then it's an insulator. It's like organic material. You have a chain of carbon. The distance is too far. There's no way the electron associated with this carbon atoms jump to another place. It does if you apply very high voltage, like 500 volt, 1000. But what's happened is material, this area, electron jump in, but it doesn't move, and it's form space charge, and electron move out from the like a polymer to the plus side, this negative side. Then this also charge, space charge. Okay, so this create a potential, positive potential and negative potential here. So this much potential difference. So if you try to flow the current, you have to overcome the space charge potentials. You have to increase this voltage even higher. Okay. If you go a certain level, then molecule structures break down. So the plastic and paper insulator usually used for battery, whatever, is once its molecule structure is damaged, then it's short circuit and current flow. Then suddenly large amount of energy flow, and it's caused fire. Okay, so the insulator is something like that. It has a band gap, and it's not clean straight. It's some areas higher level like that, but average like a 15 electron volt is considered the insulator. So how do you make a actually diode? What we do is we have a silicon and we put impurity gallium and the phosphorus. So this is the N type and this is the P type. Okay, and this is a semiconductor. So when you apply voltage plus minus, so this is a hole, the hole pushed here and excess electron is pushed here, they recombine here. Okay, so it's keep going, current flow. This is a forward current. What's happened if you galvanium that's gallium and the phosphorus, you applied the voltage other way around. Okay, then all the holes are supplied with electron and disappear, and all the electrons flow out to the positive side and disappear, right? So between them there's no more hole or electron to make it conductive. Let's create the depletion layer. So it's a hole in the electrons depleted. So the current doesn't flow anymore, and that's why this become diode. It's a forward current flow, and if you reverse the voltage, current doesn't flow. Okay. Germanium used to be used for making a diode. We call that rectifier, because that diode is used for making a radio. Germanium radio is very long time ago. They call that radio made of the germanium. A germanium radio was very popular. Okay. So what's happening if you mix this N-type, P-type, N-type? Okay, so we have this kind of device. This is called transistor. Okay, what's happening in transistor? You apply forward here, then a lot of holes in the electrons are recombined here. Without applying a voltage here, there's a diffusion layer here, and even you apply the plus voltage, the current doesn't flow. But this recombination, once you apply this voltage, this diffusion layer is going to be covered by this recombination layer. And suddenly entire layer becomes recombination and current flow. And this current, the ratio is like 100. And that means amplifier. Whatever you have a signal here, 100 times larger signal come out. This is a transistor. So you control this current by this little current. The ratio is like 100. Okay, so that's the way transistor is created. Now, how do you make a P-type and N-type? You have a silicon substrate, and you cover with oxide film. And what's happened is you increase the temperature and put the gas like gallium in the gas, hot gas. We put the gallium. So gallium it's diffuse into silicon crystal. So the silicon and gallium and the silicon is kind of crystal structures. Gallium get in, and that's called impurity. Okay, it's the same thing as phosphorus. So you make a oxidized films, make a window, and opening window get this gas, gallium gas, diffused into the silicon body substrate. So that's the way you make a P-type. Once you made a P-type, you make another one, and this time phosphorus diffuse. So it's an N-type. So N, P, and substrate has N, then NPN. This is a transistor. Okay? So that's the way they make. So the gallium, gallium, let's see, gallium, aluminum is also used to make some LED. All the band gap energy levels is important. Arsenide is used, phosphorus is used. Germanium germanium is same as silicon, but not exactly the atom size is much bigger, germanium. And that means when you create a crystal is skewed like impurity got into the silicon. And that makes the band gap level different. Germanium is used for infrared level detections and the military use, and also there are many. It's all depends on how the energy band gap is created by combination of those, combination of this area, the material. That's all semiconductor technology is. Okay. If you think this video help you to understand, and please subscribe. We have other videos. I hope you enjoy. Bye.